A growing number of galaxies seem to be bereft of the mysterious substance, posing fresh challenges for some of cosmology's most cherished theories. Astronomers have found yet another ghostly galaxy that appears to be devoid of dark matter. Researchers have reported several such sightings over the past few years, each time flagging so-called ultra-diffuse galaxies that can be as large as the Milky Way but relatively bereft of stars. This latest object, known as AGC 114905, is similar in size to our own spiral galaxy yet has 1,000 times fewer stars. If the dark matter-free status of AGC 114905 is ever confirmed, cosmologists will be forced to re-examine and perhaps even abandon some of their most cherished theories in favor of more exotic explanations for what makes up the universe's unseen mass. Different types of galaxies that are not exactly the same, measured with different techniques, seem to be telling a somewhat similar story, says Pavel E. Mansera-Pina of the University of Groningen in the Netherlands, a member of the team that studied AGC 114905. The story is one of outliers and stragglers that fail to conform to galactic norms. It would be awesome if these strange objects ultimately give us information on the nature of dark matter, says Yale University astronomer Pieter van Dokkum. An intergalactic hunt for dark matter. Dark matter-free galaxies are anathema, especially because studies of galaxies that seem to have copious amounts of dark matter are what led astronomers to posit that our universe is filled with it in the first place. For example, the speeds at which stars and gas in the nearby Andromeda galaxy are rotating around the galactic center suggest that much more matter must be present than meets the eye, providing the gravitational heft needed to keep the visible matter in orbit. Such observations led to the Lambda CDM, LCDM, model of cosmology, where lambda refers to dark energy and CDM to cold dark matter, which is thought to make up about 27% of the universe. Cold in this context merely means the putative particles of dark matter are moving far slower than the speed of light. Simulations using cold dark matter have been extremely successful at replicating patterns seen in the large-scale clustering of galaxies, as well as in the cosmic microwave background, the leftover light from about 380,000 years after the Big Bang. But the predictions of these simulations for galaxy-scale goings-on have proved somewhat harder to reconcile with astronomical observations. In LCDM simulations, galaxies form when dense clumps of dark matter in the early universe act as gravitational seeds, sucking in even more dark matter to form massive halos onto which huge volumes of gas then coalesce, birthing stars. Thus, according to the LCDM model, all galaxies should have dark matter aplenty, with most of it tightly concentrated at galactic centers. But even before the discovery of these ostensibly dark matter-free ultra-diffuse galaxies, studies of dwarf galaxies orbiting the Milky Way showed that these diminutive satellites lack the stark, central cusp of dark matter predicted by simulations. The dark matter distribution in these dwarf galaxies is smoother, forming a wider core rather than a sharp cusp at the center. Dragonfly's discoveries. In 2018, Van Dokkum, Shani Danieli and their colleagues further muddied the waters with the discovery of an ultra-diffuse galaxy called Dragonfly 2, NGC 1052 DF2. The researchers found Dragonfly 2 using the Dragonfly Telephoto Array, an instrument designed to observe large and extremely faint objects in the night sky. They soon followed this up with the discovery of another galaxy called NGC 1052 DF4. Using a range of telescopes, including the Hubble Space Telescope, HST, and the 10-meter class telescopes at the Keck Observatory atop Mauna Kea in Hawaii, Van Dokkum and his colleagues measured the speeds of star clusters associated with these galaxies. From those speeds, they inferred each galaxy's total mass, finding that normal matter, in this case, mainly stars, is enough to explain the observations. Little if any dark matter is needed. Many outside experts had doubts. There was a big debate in our case, Van Dokkum says. The controversy stemmed from uncertainties in their measurements of just how far these galaxies are from Earth, which helps constrain how much luminous normal matter they contain. Simply put, a galaxy's apparent brightness is influenced not only by its cosmic distance but also the characteristics of its stellar population. Initial estimates put Dragonfly's odd pair at a distance of about 20 megaparsecs, that is, more than 65 million light-years. But if the galaxies were instead considerably closer, perhaps only 13 megaparsecs away rather than 20, as one follow-up study suggested, their apparent brightness could be better explained by smaller amounts of luminous normal matter. The speeds of the associated star clusters would then require greater fractions of dark matter in both NGC 1052 DF2 and NGC 1052 DF4. But in April 2021, Van Dokkum's team released the results of an inch-depth HST study of both anomalous galaxies, showing that their greater initial distance estimates were correct. If anything, The galaxies are a wee bit farther away, making the case for little or no dark matter even stronger. This convinced people and, frankly, ourselves, Van Dokkum says. For NGC 1052 DF2 and NGC 1052 DF4, or DF2 and DF4, the evidence is clear: these two galaxies lack dark matter. But because both reside near a massive elliptical galaxy, called NGC 1052, the explanation may be simple: their dark matter could have been tidally stripped away by the gravity of this humongous companion, leaving behind only the normal matter. Some astrophysical processes could hasten such outcomes. In March 2021, astrophysicist Reina Campos of McMaster University in Ontario and her colleagues showed how certain types of small, dense dark matter halos forming in the early universe could give rise to great clusters of massive stars near a young galaxy's center. As these stars expired in explosive supernovae, the resulting winds and shocks would drive outflows of dark matter away from the galactic center. That would eventually expand the dark matter halo, creating a core in the center and lowering its concentration, Reina Campos says. Add to that tidal stripping, and DF2 and DF4 no longer seem so mysterious. 6 strange singletons. But the newfound object AGC 114905 adds an entirely new twist to this complex cosmic tale. In 2019, Mancera Pina and his colleagues reported their discovery of 6 ultra-diffuse gas-rich galaxies, made using the Very Large Array (VLA) radio telescope in New Mexico. The VLA observations revealed that gas clouds in these galaxies are orbiting much slower than would be expected if the galaxies harbored typical amounts of dark matter. The initial low-resolution measurements suggested that the cloud speeds could be explained by the presence of normal matter alone. Also, unlike the pair of DF2 and DF4, each of these galaxies is a singleton, isolated and nowhere near any other cosmic object that could strip away dark matter. Other astronomers were intrigued but still skeptical because the VLA observations were not strong enough to support definitive conclusions. Everyone was saying, "Okay, but now you need better data to fully convince us," Mancera Pina says. AGC 114905 was the one galaxy out of 6 that the team chose for deeper investigation. Mancera Pina and his colleagues observed the galaxy for 40 hours, using a high-resolution configuration of the VLA. Previously, they had studied the galaxy's rotation by looking at the speeds of gas at 2 locations along its radius. This time they looked at 5. The results did not change. The observation suggests that there is no room for dark matter, Mancera Pina says. The latest observations of AGC 114905 also disagree with predictions from theories of modified gravity, such as modified Newtonian dynamics, MOND. Such theories seek to explain the motions of stars and gas in galaxies without resorting to dark matter. MOND tells you directly how the galaxy should rotate, Mancera Pina says. And this prediction is completely off of our value. Stacy McGaugh, an astronomer and longtime proponent of MOND at Case Western Reserve University, is not convinced. This is one galaxy. As such, using it to make strong claims, they claim to falsify both LCDM and MOND, is overstating the case, he says. The normal behavior of galaxies is well established. That this is an outlier is more likely to be due to systematic uncertainties rather than a real physical effect. A doubtful inclination. Mancera Pina and his colleagues acknowledge that the biggest sources of uncertainty in their observations are their reckoning of the galaxy's overall shape, plus its inclination angle, how tilted it is with respect to our cosmic line of sight. This angle has an outsized influence on estimates of just how fast things are whirling about within a far-off galaxy. For technical reasons, astronomers can presently only measure how fast a galaxy's stars and gas are moving toward or away from us. Any lateral motion in the plane of the sky is impossible to discern for distant galaxies. A spiral galaxy seen face-on, with an inclination of 0, would yield essentially no information about the velocities of its stars, whereas one seen edge-on, with an inclination of 90 degrees, would allow very accurate measurements of stellar speeds. Hence, an accurate estimate of a galaxy's inclination is crucial. The team took AGC 114905 to be circular and estimated its inclination to be about 32 degrees, plus or minus 3 degrees. Yet, Mancera Pina says, if you want both MOND and cold dark matter to work, that inclination will need to be around 10 degrees, so the galaxy will need to look rounder. We have measured this as carefully as possible. And we find that the associated uncertainties of our measurement are very far away from those 10 degrees. If the assumptions about the galaxy's circular shape were off, because it is oval or distorted or has some other weird shape, then this, too, would impact the inclination estimate and thus the estimated speeds of stars and gas. This is a systematic that always leads one to overestimate the inclination, McGaugh says. Studying the galaxy with an optical telescope rather than the radio-based VLA would help reduce the uncertainty, Van Dokkum says. I hope somebody gets a Hubble image of this object, he says. Then we can see what it actually looks like. Meanwhile, Mancera Pina and his colleagues are planning to use the VLA at high resolution to scrutinize the other 5 ultra-diffuse galaxies from their initial study that have also shown similar characteristics. Benoit Famé, an astronomer at the Strasbourg Astronomical Observatory in France, argues for studying an even larger sample of such galaxies to rule out any systematic bias arising from imperfect inclination measurements. We have very good reasons to doubt the inclination measurement, which is the key to the result, he says. We should therefore wait for a larger sample size of such a putative galaxy population before throwing all our present theories of galaxy formation into the trash can. Still, he concedes that if the results are verified, the implications would be enormous. Assuming it holds, the authors are totally right to think it poses a problem to both LCDM and MOND, Famé says. If that happens, and this is a big if, the focus would shift to other candidates for dark matter. That is because the favorite explanation for DF2 and DF4, that they were somehow stripped of their cold dark matter, does not work for AGC 114905, given its isolation in space. Dark matter diversifies. One promising alternative to cold dark matter is something called self-interacting dark matter, SIDM. In the LCDM model, dark matter is considered collisionless, meaning it does not interact with itself. But if particles of dark matter can routinely collide and interact with one another, this could help explain the diversity of distributions of dark matter observed in different galaxies. In a study published in 2019, Manoj Kapilinghat of the University of California, Irvine, Haibo Yu of the University of California, Riverside, and their colleagues showed that self-interacting dark matter would redistribute kinetic energy from the outer regions of a galaxy's dark matter halo to its inner regions on cosmological timescales. Collisions between dark matter particles would, on average, increase the velocities of those nearer the galactic center, making them gradually spread outward to transform the dark matter density profile from a cusp into a core. The team showed that the observations of the orbital speeds of stars within galaxies of a number of different types, as captured in the Spitzer photometry and accurate rotation curves, SPARC, dataset, is better explained with models of self-interacting dark matter than with LCDM. In 2020, Yu and his colleagues showed self-interacting dark matter could enhance the tidal stripping effects postulated to have removed the mysterious substance from DF2 and DF4. The effect of self-interactions is to push the dark matter from the inner regions to the outer regions of the galaxy, Yu says. Once this happens, a nearby behemoth such as NGC 1052 can take over, siphoning away the dark matter from the outer regions of DF2 and DF4. The same scenario is far more unlikely if one assumes collisionless cold dark matter. But given that AGC 114905 has no nearby neighbor to explain its potential lack of dark matter, Yu and Kapilinghat, along with Mancera Pina and their colleagues, are trying to see if starting with a different initial halo of dark matter, than is usually assumed in LCDM, can provide some answers. Simulations throw up many types of dark matter halos, and cosmologists take as their starting point the likeliest halo type as the basis for further analysis. But galaxy formation could possibly begin with other types of halos that have a different distribution of dark matter. We are exploring some dark matter halos that no one has explored before. We see some promising signals, Yu says. We will study dark matter-free ultradiffuse galaxies in both CDM and SIDM frameworks to see which one agrees better with the observations. Subir Sarkar of the University of Oxford endorses using any and all means to make sense of dark matter. The landscape of theoretical candidates for dark matter is very rich, and we have had little guidance so far, either from accelerator experiments or from direct or indirect searches, to narrow down the possibilities, he says. Any indication that dark matter has self-interactions is very interesting, as this immediately argues against popular candidates like CDM, as well as against MOND. So the importance of these observations and the need for better understanding of galaxy formation with such non-standard dark matter cannot be overstated.